So we've been talking about ideal gas mixtures. Last time we had application for a closed system analysis, ideal gas mixtures, as well as an open system analysis. Those problems can be challenging. Make sure you work them and are prepared. But now we move into the study of moist air psychrometrics. So you, like me, probably when you're introduced to a new word, you're not exactly confident what is the definition or meaning of this word. You'll Google it, you'll look at a Wikipedia definition or an online dictionary. I used to have dictionaries on the shelf, but now it seems like everything's online. So psychrometrics, the Wikipedia, it's not to be confused, and that's why I spend a little time early right now talking about what it's confused with, not to be confused with psychometrics, which is a discipline, psychology and education, but it's either psychrometry or psychrometrics. Those words are used to describe moist air. I remember when I was first introduced to it, the term, you get confused. It's like, are we talking about something psycho, like a 1960s slasher thriller movie? No. Are we talking about psych? A TV program that a few students will every now and then say, I saw it, but I personally never did see an episode of it. How many people remember this one? Couple? All right. Yeah, that's about the right percentage that I usually get. About 10, 15, 20% of the class says, yeah, I've seen something like that before. Well, we're studying moist air. Here's a question for you. Blank is the study of moist air. Psychrometrics or psychometrics? All right, so what's the probability that the class is 100% correct? There's always one, isn't there? Well, for those that got it right, what was the difference between all of these letters in these words? I mean, what is the... Look for that R. That's right. Look for that R. So let's go ahead and close that. Let's do this. Blank is the discipline of psychology and education. I'm not kidding you. This is easy. I want 100% correct this time. But do you think I'll get 100% correct? Somebody's not going to give it to me. They know. It's like, Professor, I am the thorn in your side. I'm going to be wrong every answer. And let's see. What do you think? 100% correct?
Yes. No.
There is always one. I think they're just tormenting me. All right. Now, sometimes you can study the etymology or the beginnings or the history of the word. Etymology, that's what that is. And so psychrometrics with the R. Do you think it's Latin in root and that it's kind of the combination of something that means crazy and acting in Latin? Or Italian and dark and cold? Or what's your best pick? Is it Greek, Russian, German, Italian, Latin? What? I did. I come up with all my questions. So, all right. Almost everything in science and engineering, what letters do we use? Do we use Russian and German letters in our symbols? Like what's rho? What's omega? What's lambda? Are those Italian letters? All right. So in the deduction, you're pretty good as a class. You're right, it's Greek. And I don't know Greek, so I'm not going to say like, oh, it's this word meaning cold with this word meaning something like to measure something. Okay. Now we talk about air. You can have dry air, you can have saturated air, and you can have moist air. Dry air is the combination of nitrogen and oxygen and a bunch of other little things But if you wanted to just approximate dry air, it would be 0.79 nitrogen, or 79% nitrogen, and 21% oxygen. And pretty much the carbon dioxide and argon and those they're not as dominant. This is approximation for dry air. Okay, is there any H2O in dry air? No, so there's no water vapor in dry air. Yes, sir.
Is this molar?
Yeah, these would be mole fractions. That's right, not mass fractions. So Y of N2 would be 0.79 and Y of O2. That's a good approximation for dry air. Okay, then you have saturated air. What do you think is the meaning of saturated air? It has the maximum amount of water. Now, is that water in the air going to be in the liquid state or the vapor state?
Vapor.
Vapor. So it's going to be the maximum amount of H2O vapor. And that water behaving in the vapor state will behave as an ideal gas. Now, nothing's a perfect ideal gas. Some are extremely, extremely, extremely close to being an ideal gas. This one, surprisingly, water vapor is a very good, close to being a perfect ideal gas. Okay, so we'll treat it as an ideal gas like everybody else does, the water vapor in it. So you can talk about the mole fractions of the nitrogen, the mole fraction of the oxygen, and now the mole fraction of the water vapor in the saturated air. Well, if this is maybe 2%, what is the sum of these two? That has to be 98. And if they're staying the same oxygen-nitrogen proportion, it's probably, for this one, I didn't leave enough room, but it's probably 0.98 of 0.79. A little bit below 79%. It'd be whatever it is, okay? And this one, what would that be? 0.98 of 0.21. A little below 21%. Okay. So that's what it means when you have saturated air, you have the maximum amount. Well, how do you know what is the maximum? Well, you can also think of the partial pressures. You could think of if I come up here and I say, go back to dry air, what's the partial pressure of the nitrogen in the dry air? If the total pressure is 100 kilopascal, to make life easy for the math, 79 kilopascal, and the partial pressure of the oxygen would be 21 kilopascal. The partial pressure is the mole fraction times the total gas pressure. And I just picked a nice, easy total gas pressure of 100 kilopascal. Now, if we come down here, the total gas pressure is still 100 kilopascal. What is the partial pressure exerted by the water vapor in that ideal gas mixture known as saturated air? It would be 2 kilopascal, true? And then this one would be, for the oxygen, it would be a little less than 21 kilopascal, and likewise, this one would be a little less, the nitrogen, a little less than the 79 kilopascal. You just multiply it by that 0.02. Well, for saturated air, this partial pressure of the vapor is the maximum possible. You can't get any more water vapor in that air. What will happen if you try to put it in? It'll condense out. It'll form into little water droplets, and then under the presence of gravity, settle out. So this is the max. What do you think this maximum partial pressure of the water vapor is in saturated air? Just a wild guess. Yeah, and now let's do this. Maybe I should ask this question. If the temperature of the air goes up, do you think the maximum possible partial pressure of the water vapor would go up or stay the same? You think hot air can hold more water? You know it can. And do you know what? Cold air, really, really cold air, even though it may be saturated, is very dry. you can still get that static friction walking across the carpet on a cold winter day, even though it may be saturated air. Just it can't hold a lot of moisture when it's cold. So anyway, this is going to be a strong function of temperature. What do you think is a strong function of temperature? It's the saturation pressure. If somebody said, I have dry air, or I have saturated air, it's 25 degrees C. Can you get me the maximum partial pressure of that? Well, you would say, I'll go get the saturation pressure. Where would we get the saturation pressure? True. It's that first table, A2, that we really spent a lot of time in that column. So you just look down and you're given temperatures, and then you're given the saturation pressure. All right. Now, what do you think moist air is in comparison to dry and saturated? It's in between. It's not saturated and it's not dry. It's in between. So the actual partial pressure of the water vapor will be between 0, when it would be dry air, and the maximum, which would be the saturation pressure for that temperature, which would be saturated air. All right, so we had the concept dry, saturated, and moist air. You ready to press forward? All right, these are behaving as ideal gases. The water vapor behaves as an ideal gas. The oxygen behaves as an ideal gas. The nitrogen, we lump dry air together, and that behaves as an ideal gas. Okay, and then we remember the ideal gas equation. If I have the ideal gas equation, PV is equal to mRT, or P lowercase script v is equal to RT, or P equal to rho RT, or P molar mass equal to rho R bar T. Are all these good versions of the ideal gas equation? So if I take this one and I have rho is equal to PM divided by R bar T. All right, help me a little bit. I'm talking about the partial pressure of a component. The density of a component, so I'll put a subscript I. That could be for the vapor, could be for the oxygen, could be for the nitrogen, or just call it dry air. It would be the partial pressure and the molar mass, but there's only one R bar and there's only one T. There's no subscript I that belongs on the R bar or T, true? So we look at this equation. Does it look good? Is it true or false? Well, let's not even do clicker, huh? I'm afraid I can't get 100% correct. It's true. It's true. That equation's true. Does it make sense? We can use it a lot, this equation. Let's now do a clicker question. How does that mass density change if only the temperature goes up, is increased? How does rho change if T goes up? Rho will not change. Rho will increase. Rho will decrease. What will it do? All right. Well, I'm not going to worry about the one student who doesn't want to play today. So we just press forward here. But the old concept, hot air rises, cold air sinks. Hot air for the same pressure is less dense. It buoys up, buoys up. All right. Now, what we're going to talk about is changing the molar mass. So if somebody says, I have a mixture, let's say water vapor. What's the molar mass of water vapor? Around 18 kilograms per kilomole, true? Maybe I say I have a molar mass of something that's about 120 kilograms per kilomole, and it behaves as an ideal gas, and it's mixed in or piped in or added into the air. What's going to happen for the lighter or the denser material? So here we go. How does the mass density change if only the molar mass goes up? Yeah, the density will go up. The density will go up if you don't change temperature. Well, this brings into a general concept in engineering that hopefully you don't leave without it, right? So somehow I have a piece of machine right here, and it has some possibly toxic material, and there's a leak that develops in it. And it's not like there's a big air conditioning system or a lot of wind blowing through it. It may be an enclosed basement or something, not a lot of circulation. If it leaks, it could settle on the floor. And then if a worker bends over, they could get a bunch of it, and then they could pass out, lay on the floor, and then really be in trouble, because that's all they're going to be breathing is that toxic, heavy ideal gas stuff that leaked out. You ever heard of scenarios like that? It's very common in safety. Or it could be that it leaks out and it's light, and hence it'll go up to the ceiling. In a fire, what do they say when you want to crawl out of a house? Go down, breathe on the floor, go out that way. That's temperature. Really, it's temperature. Anyway, so hot gases go up, but if it's the same temperature, if it's high molar mass, it'll sink. Okay, what do clouds do? Do clouds float in the sky and go up higher, or do they sink around your house and just create a continuous fog around your house? Yeah, so take a look. What is this? Water vapor compared to about 29 kilograms per kilomole for dry air. Water vapor will tend to buoy up. Same pressure, same temperature. It's lighter. It goes up. All right, a question. I have 1 cubic meter of dry air. It has so much oxygen in it. I want you to compare that to 1 cubic meter of saturated air at the same total temperature and pressure. So the question or statement is that 1 cubic meter dry air has more oxygen than the saturated air? True? False? Or I need more information? All right, so maybe we want to do this quantitatively, true? So you could say, using the ideal gas equation, the mass of some component is equal to the partial pressure of that component, the molar mass of that component, divided by R bar T, and I left the V out, didn't I? Let's put the V, and then the molar mass of that component. Does this look okay? All right, let's do this one. Let's say the mass of oxygen is going to be the partial pressure of the oxygen times that volume that you have times the molar mass of the oxygen divided by R bar and T. So we're going to say that we have case 1, we're not going to change this temperature, we're not changing R bar, we're not changing the volume, we're really not even changing the molar mass of the oxygen. But we think about the partial pressure of the oxygen in dry air, and we compare that to the partial pressure of the oxygen in saturated air. Are they the same? No, they're not. Does that help us? Which one do you think is going to be greater? No, let me not answer that one. It'll give away. Let's re-ask this question. 1 cubic meter of dry air has so much oxygen. Does that amount of oxygen, is that more than 1 cubic meter of saturated air? All right. Well, I didn't get everybody. So, if you have dry air, maybe your grandparents, or as you get older, your lungs, actually the doctor can gauge the age of your lungs. I one time went and had a stress test and all that. So, congratulations, this part of your body is doing really well. Let's now talk about the other parts of the body. But before he talked about the other parts, he said, your lungs are like a 25-year-old man. Great, good. So, but as you get older, what happens? People like to move to dry climates. They like to be in Arizona, or, where they can easily breathe. It's dry. You ever seen somebody when they're old and they're having trouble breathing, because especially on a hot, humid day in Houston? No? Anyway, they go into air conditioning and then well, some of it is breathing. But anyway, there's more oxygen. There is more oxygen when there's less water vapor to displace it. the water vapor takes up room. All right, how did we do before? About the same. All right, that's 25 correct, 26 correct. I only convinced one person. Oh well. All right, this is a humbling day for me. It's a very humbling day. Another question. The molar mass of dry air is around 28.97. All right. The molar mass of moist air that has 2% mole fraction of water vapor, is that going to have a lower molar mass? It's going to be less than 29.7 or equal to 29.7 or greater? What's going to be the new molar mass? I'll give you a little extra time. There. Okay, let's do this. Last time we said that the molar mass of the mixtures, and the book sometimes doesn't put a subscript on mix, they just put cap M for the molar mass of ideal gas mixture, is equal to the sum of Yi times Mi. True or false? True. That's true. And we're going to have so much of the nitrogen, so much of the oxygen, and so much of the H2O, if I can write H2O. And now you compare dry air with moist air that has so much water vapor. True? So the molar mass of the dry air is 28.97. You bring in the molar mass of H2O. I have to compare that. What is it? Around 18 kilograms per kilomole. You're bringing in lighter. So what's going to happen? You can actually get that, okay, well, it's going to be 98% of this, 2% of that. It'll be around 28.4. It'll go down. The molar mass of that moist air mixture will be less than the dry air. All right, let's grade it. All right. Well, did my explanation help, though? All right, let's press forward. Now that we have mastered dry air, moist air, and saturated air, let's move on to more difficult concepts of dry bulb temperature, wet bulb temperature, and dew point temperature. Now the dry bulb, if they have a temperature with no subscripts, that's the dry bulb temperature. Somebody says, what's the temperature in this room? You say, oh, about 75 degrees F, right? That's the dry bulb temperature in this room. It's as if I looked at a thermometer and the bulb of the thermometer was dry. If it's wet, though, what happens if I have a thermometer and the bulb of the thermometer is wet? Well, you're not going to get a good reading on that thermometer until it dries off and becomes dry. Because while it's wet, it could be doing this, evaporating. The water could be evaporating off of the bulb. When it's evaporating off the bulb, do you think this will sense a higher temperature or a lower temperature? Lower. The wet bulb will be less than the dry bulb temperature because of the evaporation, the cooling effect of evaporation. Everybody in the summer takes a t-shirt, they douse themselves all wet, and they run around because they want to experience that evaporative cooling. Well, it works on thermometers as well. So that's our wet bulb temperature. There's a device. It's called a sling psychrometer. I used to have one. I passed it around for a couple of semesters, if not years, in Thermo 2. And then last time I passed it around, it came back in better or worse condition than I heard. What do you think? Well, I was saying, everybody, please make sure and sling it around. Get a feel for it by taking your hand and making it twirl in a pattern like that. But then they hit stuff with it. Smack, smack. Usually your neighbor's head. But anyway, it came back with the bulbs busted. But then I don't have it anymore. It's broke. Sorry. But you have two bulbs. One is covered with a wick material, which goes into a reservoir that you fill with water. So you can keep it wet while you're slinging it around. And you fill it with room water, or you let it sit for a long time so the water is the same temperature as the room. But once you start slinging it, it starts to really evaporate. It's forced convection evaporation. And then that temperature on this thermometer is less than that one. Then you look at you can read the lower wet bulb temperature, and you can infer the humidity in the room. All right, we'll get to humidity next, but that's the wet bulb temperature. The other one is the dew point. This is probably the most challenging or difficult, but you have the most experience with it in your life. You ever walked out in the morning, go across grass, it's all wet? The sprinkler wasn't on. Where did the water come from? From the air. It dewed out of the air. In the car, in the morning, you turn on the wipers to clean the windshield because it's all wet, moisture. Where did it come from? The air. You park in a garage, same windshield, same, but it's not there, right? It's got to dew out. If you park under a tree, a lot of times, it won't dew out heavily on your windshield. But this is what's happening. Everybody has experience with the dew point temperature. Here's another example. You walk out, cold winter day, you take your breath, and you pretend you're a 10-year-old like you're smoking. You just go, and what do you see? A white cloud? That's all that moisture in your air that you're exhausting hitting that cold air, and it's below the dew point temperature, and so it then condenses and makes water droplets. Sometimes they'll have this thick fog on highways, creates real big traffic accidents, right? And then a couple hours later, there's no fog. Well, the temperature passed through that. Now it's heated up and there's no more fog. But they'll have all these pile of cars. So anyway, in fog-prone areas, that's what's happening. You go through that dew point temperature. Actually, most days we go through it twice a day. Because in the early morning hours, let's say it's midnight to 6 a.m., somewhere in here you're hitting the bottom of your temperature, and then you're starting to warm up when the sun comes up. And then it never ends in August. It's just always 8 o'clock at night. I'm still baking. But anyway, but it goes like that. But you'll probably hit where it starts to dew out, and then it comes back, right? So it'll be dewing out for a couple hours late while the temperature's dropping in the morning. All right. So how do we quantify this? Well, it's when, as you drop that temperature, that you hit the dew point temperature. But conceptually, we can talk about the dew point temperature of the air right now in this room. So theoretically, we would say, well, the dry bulb temperature of the air in this room is about 75 degrees F. But if we took the air, didn't change the pressure, and just cooled it, if we got it down to maybe, 62 degrees F, it would start to dew. Well, that would be the dew point temperature. We don't have to take it to 62. We can infer what we would need to take it to. So you say this. You say, what is the actual partial pressure of the vapor in the room, in the air, right now? Okay, I calculate that. Usually I calculate it using humidity calculations, which are the next discussion. And then I say, if I take and find the saturation pressure at that particular temperature, which gives me the exact value of the current vapor pressure, then I'm going to call that temperature the dew point temperature. You have to work a few problems. I've never found this an easy way to explain it. This is kind of a crazy equation. It's like the saturation pressure is a function of temperature. Yep. Find that particular temperature, and we'll call it the dew point temperature, where it gives us the saturation pressure is exactly the partial pressure of the water vapor in the current moist air mixture. Here's a question. Is the wet bulb temperature less than the dry bulb temperature? No, why? Why is the wet bulb temperature less than the dry bulb temperature? Evaporation from the dry bulb, condensation from the dry bulb, evaporation from the wet bulb, condensation from the wet bulb, depends, need more information. All right, we're in. How do I get more people to be correct? It's not that good. All of these are your colleagues. Everybody should think about everybody else in this room as if you want to work with them as part of their career, your career. You ever worked with somebody in a company and it's on a team and they let you down? You don't want to work with anybody like that. Come on. 4 people. Why do you have that wrong? Maybe the thumb. Your neighbor pushed it. That's all I can say. Your neighbor reached over and pushed it when you weren't looking. And just to embarrass you. True? Yeah. All right. Let's do another one to redeem yourself maybe. Evaporation cools the wet bulb. True or false? Let's see how many people are playing with me on this one. Yes. Yes. There we go. I can do it. I can get everybody to pass. Another one. Evaporation from the wet bulb is more vigorous if the surrounding air is saturated air. Everybody in? All right. So what do we mean by this surrounding air? You take the sling psychrometer and you're twirling it. You're in some medium, right? That's the air that you're slinging it around, that you're getting the reading from. True? That's what you mean by surrounding air. What does saturated air mean? That is maximum water that's saturated. Saturated air, it's maximum water. So evaporation from the wet bulb, this is a little intuitive, right? But do you think let's say I'm in Houston, I'm really hot. Somebody says, douse your t-shirt with water. You think it's going to cool you a lot if it's saturated air? Let's say you're in El Paso. They douse the t-shirt with water. Guess what? You're going to get cold. Not only is it, you breezy and it could be hot outside, but there could be a lot of evaporation. Why? What's the difference between El Paso and Houston in the middle of summer? One's a desert, one's a swamp. Yeah. And so the surrounding air in Houston's saturated, the surrounding air in El Paso's dry. True? So dry air makes it more vigorous in the evaporation. And so let's just grade it. Congratulations to 70%. Or 70, whatever that is. 78%. Almost 80. 80%. I'll round that off. I feel better now. What is more common or most common? Is it that the wet bulb's less than the dry bulb? The wet bulb equal to dry bulb? The wet bulb greater than the dry bulb? Or, hey, I can't tell. Need more information. So let's take a look. Did I tell you, 2 people in this room, did I tell you that I can look at your name and see how you did on every question? Yes, I can. Yes, I can. So, come on now. The wet bulb is going to be lower evaporative cooling. There's not evaporative heating that I know of on that bulb. All right. Let's do one more or not? All right. When the wet bulb equals the dry bulb temperature, the air has either very little water vapor, air has considerable amount of water vapor, or it depends. Sorry if I didn't give you enough time, but we have to grade it. True? All right. It has a bunch of water in it. Not only, when does this happen? When does the wet bulb equal the dry bulb? When I have no incentive for evaporation. When the evaporation rate kind of goes to zero. When it goes to zero, when the air can't hold any more water vapor. If it's saturated, there's no potential to evaporate. That's why Houston feels so muggy, right? So this is when you have saturated air, the wet bulb is equal to the dry bulb. Make sense? So you have a considerable amount of water vapor. That's true. All right. That's the best answer. It is possible that the wet bulb temperature equals the dry bulb temperature equals the dew point temperature. True or false? Can you get a circumstances where the wet bulb equals to the dry bulb equals to the dew point? Yes, that's possible, or no? I honestly feel I must give you more time because the number of incorrects were cut in half by that additional 20 seconds. That has to be it. It's my fault for not giving you more time. That has to be it. Seriously, I can look at the counters. I know where you're coming in on your responses. And there were 10, and I got 20 more seconds. Now it's down to 5. Not bad. I'm an educator. Give more time. Give more time. Do that for the test. Okay, when is the wet bulb equal to the dry bulb? We talked about that. It's when it's saturated air. And then what about this dew point? It's right there at the cusp to begin the dew. If it's saturated air, the dew point is equal to the dry bulb equal to the wet bulb. All three are the same temperature if it's saturated air. Okay, I don't know if this one's more challenging, but we'll try it. If the wet bulb temperature equals the dry bulb temperature, then the dew point is less than the dry bulb, equal to, or greater than the dry bulb. Do you need more time or not? I'm going to try that. I don't think I've given enough time. This is also a good strategy. You just show how your neighbors are voting. Usually see, it helped a few. So the dew point would equal the dry bulb, which would equal the wet bulb when the wet bulb is equal to the dry bulb. All right. All right, now we talked about dry air, saturated air, moist air. We talked about 3 temperatures. We have to talk about 2 humidities. One you're extremely familiar with. It's called the relative humidity. If somebody says it's 45% relative humidity today or 30% relative humidity, somebody give me an estimate of the relative humidity of the air in this room right now. 35 to 55%. If it starts getting over 55, you start to notice it, right? And you can walk into, I went into a bathroom it was cool, but it was too moist. It was like, so you can have it, especially where there's water sources, sinks, and other water sources in the restroom, or a coffee pot in a kitchen, you can have a higher humidity there. After a shower, absolutely, yep. Higher humidity there. So with this relative humidity you're very familiar with. This humidity ratio is the one that the engineers love. You like this. Once you're familiar, introduced to this one, it's the humidity ratio that you're going to like. But what is the relative humidity? Well, the relative humidity is typically defined as the mole fraction of vapor currently in our moist air divided by the maximum mole fraction if it would be saturated air at the same temperature. And you're not going to change pressure either. Same temperature and pressure. Okay, that kind of leaves me a little cold. But if I take that mole fraction and I multiply by P, and I take this mole fraction maximum and I multiply by P, I didn't change the equation, but what do I get in the numerator? I get the actual partial pressure of the water vapor in the moist air. And what do I get down here? Well, I get the maximum, which is the saturation pressure at the temperature. So this is the way we really use it, even though maybe theoretically it's defined as a ratio of mole fractions. It's really the ratio of partial pressures. All right. So a lot of times you'll see it unraveled. You'll see, the actual vapor pressure of the moisture in the water vapor in the moist air is the relative humidity times P sat, the saturation pressure at that temperature. Okay. All right. What is this humidity ratio? You're going to look at this definition and you say, I don't like it. Why do the engineers like it? It's the mass of vapor per mass of dry air. Not mass of moist air, just mass of only dry air. So only the oxygen and nitrogen, the dry components of the air. You say, that leaves me kind of cold. Let's take a look at the units for a second. Kilogram per kilogram. It's really dimensionless. And a lot of times, they'll even just leave it dimensionless. But it's kilograms of one type of mass, water vapor, per kilogram of the other type of mass, which is dry air, which is just the nitrogen oxygen. So I'll emphasize sometimes it's kilogram vapor per kilogram dry air. All right, just like up here, if you wanted to, you could take that mass of vapor and you could divide by, well, let's do this one. Let's go over here and play with our ideal gas equation. There's a lot of variations of it, but let's do P molar mass V equal to M R bar T. All right? So if I wanted to, I could say the mass of some component. Let me just add the subscripts right now. I, and I. Okay? So the mass of component I would be the pressure, the partial pressure of that component, the molar mass of that component, the total volume of my ideal gas mixture, divided by R bar T. So what we can do is replace this mass of the vapor, because you're thinking, I'm going to focus on a particular volume of this moist air, and I'll have the partial pressure of the water vapor, I'll have the molar mass of the water vapor, I'll have the total volume, I'll have the R bar T. I'll do the same thing for the dry air. I'll have the partial pressure of the dry air, I'll have the molar mass of the dry air, I'll have the volume and the R bar T. Do we have any cancellation? A lot. And so the humidity ratio you can work out is equal to the molar mass of water vapor divided by the molar mass of dry air times the partial pressure of the water vapor divided by the partial pressure of the dry air. All right. What is the numeric value for the molar mass of water vapor? About 18.02. What is the numeric value for the molar mass of dry air? 28.97. Then you still do PV over PdA. If you have a calculator, you'll run that. It'll be like 0.622 PV over PdA. And in a lot of books, they'll just like, that number 0.622 falls out of the sky like pi. There it is. Memorize it. No, it's the ratio of molar masses. If you have a calculator, check me. But a lot of times they'll just show you this equation and it's like, where did that 0.622 come from? Well, this is where it came from. That's the humidity ratio. All right. I don't know if I got enough time. No, I don't. Well, thank you very much for your attention. We'll pick up here next time.